This video is about solving trigonometric equations by factoring. As always, begin by reading carefully through the textbook and taking good notes, but now consider the following highlights for this topic. We're going to begin by recalling several things. The first is something called the zero product property, and this is an idea in algebra that you may have seen or maybe you forgot by now. But it goes as follows. If you have a product, which I'm just going to use A times B to represent. You could use any different variables if you'd like, but A times B, and you have that product equal to 0. So I'll say A times B equals 0. Then that implies a couple possibilities, right? If you have a product equal to 0, then perhaps one of those factors is 0. Well, that would mean that A could be 0, or it could mean that B is 0. You see, either of those could be 0, or both could be 0, and that's the only way to get a product that's equal to 0. You have to be multiplying by 0 in one of those factors. So that's known as the zero product property. You may recall that from algebra. Secondly, we're going to recall factoring methods. Now, there's a whole bunch of these. If I remember, I'll try to put a link in the video description, this video's description, taking you to some more resources I have to review those. There's a whole bunch of them. We're going to have to use them, and so you may need to review a lot if it's been a while or you feel rusty on those. Or thirdly, we're going to recall unit circle values that we've been working with. So this is the same old unit circle and the basic trigonometric function, or basic trigonometric equations that we did in the previous topic. And then we're going to put this all together. So at this point, we're going to be looking at more advanced equations that we can solve with a combination of any of these known methods or facts. Now, until the unit circle is easily memorized, I do recommend continuing to write it out by hand. And again, until you feel very comfortable with it. Even writing it out and then having it beside you as you do these problems can be a good way to practice using it so you get faster at that and more comfortable with it. But it's definitely going to be the foundation of what we're doing in these problems. Let's jump in with some examples where we want to solve the given equation. That's all we're told. And the first example we have begins with a product of two parentheses that's equal to 0. So in the first set of parentheses, we have tangent squared theta minus 4. And then in the second set of parentheses, multiplied right after that, we'll have 2 cosine theta plus 1. And when you multiply these two parentheses together, the result is equal to 0. And our goal is to solve. Well, notice that this is set up pretty much exactly as the zero product property we had above. So if I think of the first set of parentheses kind of like the A, and the second set is like the B, then this is kind of like the A times B equals 0 thing we had above, which means this implies, or we could say that directly implied from where we're starting here, by the zero product property, would be that either of these could be 0. So tangent squared theta minus 4, that's the first factor. That could be 0, just like A could be 0. And then the second factor, which was 2 cosine theta plus 1, that could be 0 in the same way that B could be 0 above. So this is just using the zero product property directly. Now, what we'll do is solve each of these, which is really like the basic trig equations we were just doing in the previous topic, right? So if I first start by trying to get the trig function alone, for example, in the first equation, tangent squared theta minus 4 equals 0, we could just add 4 to both sides. The 4's would cancel, leaving us with tangent squared theta on the left side equals 4. And then we're trying to get the trig function by itself first. As you may recall, we've done this. You can take the square root of both sides of the equation, which will take it from a tangent squared down to a tangent theta, but at the cost of a plus or minus that has to show up on the other side from algebra, as we recalled there. So we now have tangent theta equals plus or minus 2. Now, from there, we can try to solve for theta. We'll do that in a second. But before we do, I'm going to go on to the other factor we had set equal to 0 and do a little bit of work on that one as well. So we had 2 cosine theta plus 1 equals 0. In the same way, we're going to get the cosine theta by itself first by subtracting 1 from both sides. This will give us 2 cosine theta equals -1. And then if we divide both sides by 2, of course, that'll give us cosine theta equals -1/2. Now, remember, we're trying to use the unit circle anytime we can because it has convenient exact values. Or I guess you may argue that they're not convenient, but there are certainly exact values that we can use as opposed to rounded decimals. Now, what we're seeing in the first result, when we had the first equation equal to 0, the tangent squared theta minus 4 equal to 0, and then we solved for tangent, we ended up with tangent theta equals plus or minus 2. If you look back at the unit circle, you'll recall that 2 plus or minus is not a value for tangent that we have on it. We have like, square root of 3 over 3 or square root of 3 or 1 or undefined and some things, but 2 plus or minus is not on there. So that's okay. We've dealt with this before, and what we'll have to do is use a calculator in order to calculate theta. So we'll say theta equals tangent inverse of, and really we're going to use plus or minus 2. We'll see in the calculator that we can just do one at a time. That'd be like taking the tangent inverse of both sides of the equation, and what we're going to get is a value for each of those. So let's take out our graphing calculator and punch this in. We'll press second and then the tan button for tangent. So second tangent gives us tangent inverse, indicated by the little -1 looking exponent thing. We want the tangent inverse of each of these values, -2 and +2. I'll just do one of them at a time. So I'll put in -2 first. Tangent inverse of -2, hit enter, and we'll get -1.11. We could say if we round it to 100, we'll do the same kind of thing for the other inputs. So second tan, but this time +2. And when I hit enter, I'll get +1.11, again, a rounded value to the 100th there if I use that. So we have plus or minus 1.11 as the result for theta. Now, we're trying to account for all solutions here. You may recall from our previous section or previous topic on the basic trigonometric equations, we have to account for the infinitely many that there actually are here. So we're going to say theta equals, and I'm going to say -1.11. That was one of those values that we got directly from the calculator. However, as you may recall from that basic equation video, we have to add or subtract multiples of the period of the function in order to account for the other possibilities which go on forever. So what we'll say is -1.11 plus, and then the way we said it before is k times the period of tangent, which happens to be pi. So we'll say here k is an integer, where we say k is an element of the script z numbers, the integers is what that represents. And so we have theta equals -1.11 plus k pi. That represents an infinite number of them, where k is 1 times pi, 2 times pi, 3 times pi, or -1 times pi, -2 times pi, 0 times pi. Any integer is what k is, which represents an infinite number of actual solutions here. Now, the same would be true for the other value we got from the calculator. So I could also say +1.11 plus k pi for the same reason, where the calculator had originally given us the negative and positive version of this when doing the tangent inverse, as we saw. So really, we have two possibilities to represent the infinite number of solutions we're getting from this part of our equation, this first factor equal to 0. If we move over to the second factor, this is where cosine theta was equal to -1/2, as we had just solved. We're wondering where that occurs. Again, you can kind of just start within one wrap of the unit circle. Sometimes it's helpful to draw a little diagram of that. You may have it already fully drawn next to you or near you if you've done that by memory, just as practice. I'm going to just resketch a little unit circle diagram here to help us out with this. So where is cosine theta equal to -1/2 is the question. Now, if you go back to the unit circle that we know and all those terminal points we have, you'll notice cosine is negative in quadrants 2 or 3, the left half of the unit circle. And -1/2 would occur at the first place in quadrant 2, near the top of the circle, and at the third place in quadrant 3, near the bottom of the circle. And if we can remember where those are, or what places those are in terms of angles, the angles that would extend are as follows. For the first one, near the top of quadrant 2, in that case, we would say theta is 2 pi over 3. Again, that's just going back to the unit circle. For our other possibility, where cosine theta is equal to -1/2 on the unit circle, just within within one wrap of the unit circle is where we're starting here. So we already have 2 pi over 3 is the first place. If you keep going down to quadrant 3, starting from the right side all the way around to quadrant 3, the third place, the third marking in quadrant 3, that would be 4 pi over 3 for that location. That's how far it takes to get there, starting from 1, 0 on the right side. And therefore, we have these two starting places within one lap or one wrap of the unit circle that we can use. What we'll then do is say, well, the period of cosine happens to be 2 pi. Therefore, I could add or subtract any multiple of 2 pi to these to get more solutions going on forever. Again, with k being an integer, we can then say this is plus k times 2 pi. In each case, again, given the fact that 2 pi is the period for cosine, therefore adding multiples of 2 pi will get us more solutions going on forever for any integer value k being multiplied by those. All right, so we can represent then any of the solutions to this original equation as one of these 4 following representations, where you pick one of the solutions we found within one lap of the unit circle, but then add the period of the function beyond that to account for all of the infinitely many solutions. All right, let's move on to another example. Number 2 is going to begin as follows. We have 3 sine squared theta minus 7 sine theta plus 2 equals 0. Now, what you'll notice is that this one, unlike the first one we just did, is not in factored form. What do I mean by factored form? Well, remember, factors are multiplied together, and the first one had 2 sets of parentheses already multiplying together, but this second one, the second equation, does not have that. So we're going to have to do a little bit of work to get it in that form. Now, I want you to recall, before we get into the trigonometry of this, that if I had something very similar to this, but in algebra, as 3a squared minus 7a plus 2 equals 0, where I'm just kind of rewriting the original equation, but instead of the sine theta, I'm just writing the letter a. This will actually simplify what we're looking at, and I think allow us to recall the factoring with a little bit less clutter in our screen here. So if I replace the sine theta with a, simply writing this equation as 3a squared minus 7a plus 2 equals 0, then notice that equation we may recall from algebra that we could solve if we just factor the trinomial that's on the left side. Now, as far as a method to factor the trinomial, this will go back to the algebra and review some things that you may or may not have fresh in your mind. So I'm going to review that a little bit here, but you may need more work on this if this feels extra tricky or rusty. So here's what we'll do. To guess and check our way through this, which is one of the ways you could factor, we're looking for 2 terms to put in the front of our parentheses, such that when I multiply them together, I get the first term in this trinomial, 3a squared. Right? Well, it turns out that 3a and a, if I multiply those together, would give me 3a squared. So let's start by putting those in front of our 2 sets of parentheses, 3a and a. And then, looking forward, I have to also put in 2 more terms behind those, such that when I multiply those together, I get positive 2, the last term in our trinomial here. Well, thankfully, there aren't too many ways to get positive 2, so we'll have a limited number of options. However, where the guessing and checking comes in is that we have to put something in here so that when I actually FOIL out the result by multiplying those 2 new binomials together, I also account for the middle term, which is negative 7a. So think about that. To get a negative 7a there, I'm definitely going to have some negative involved with these next terms. So let's try this. If I put a -2 and a -1 such that I end up with 3a minus 1 as my first factor in parentheses, and then after it in parentheses a minus 2, let's now check this to see if it works. If I FOIL, remember FOIL is first times first, that'd be 3a squared. Outer would be 3a times -2, that would be -6a. And then inner would be -a or -1 times a, which is -a. So if I put those outers and inners together, this is where the checking comes in for guess and check. I have to combine all those like terms. Well, outers is -6a, inners is -1a. Guess what? That gives us the -7 we want in the middle, so those actually work. If you ended up not getting that term, you might want to rearrange the -2 and -1, right? There's some variation that you might need to go through to find those that work, assuming that it is factorable. Now, what we end up here with is 3a minus 1 times a minus 2 equals 0. Now, that's great because that's how you could factor this algebra problem, but that's not what we're actually working with in our trig problem. So what we'll do is take our original problem of 3 sine squared theta minus 7 sine theta plus 2 equals 0. That was the original problem. And what we'll do is write it now in factored form. We've already done the hard work on the factoring. We just got to substitute sine in for a that we had done in our little recall algebra review here. So I'm going to put, instead of 3a minus 1, we're going to put 3 sine theta minus 1. And then instead of what we had for our second factor, a minus 2, we'll put in sine theta minus 2. And we can now be confident that if we FOIL or multiply these together, we will get the original left side of the equation here. And of course, you can always double check that if you'd like, just to make sure you've got that, either just with the algebra, factoring review, or with the actual trig. All right, well, what we have now is something of the form a times b equals 0. This is the zero product property we were looking for. And what this means is we have two possibilities. Either the 3 sine theta minus 1 factor could equal 0, or the sine theta minus 2 factor could equal 0, right? This is just using the zero product property. All right, well, let's unpack this a little bit more. This would mean sine theta. If I just solve for sine theta by adding 1 and dividing by 3, I'd have sine theta equals 1/3. For what are my results? Other side, if I just add 2 to both sides, I'll have sine theta equals 2, positive 2. But if we think ahead just one step, can the sine of theta ever equal 2? Well, go back and review the range of sine. The highest it gets is 1. Or the lowest it gets is -1 in terms of the just unit circle values. So actually, we're not going to get any solution out of that side, so we could just kind of mark that as no solution and move on. It doesn't mean the whole problem has no solution. It just means that that branch of our work is not going to yield a solution. So we'll go back to the other one we had, which was sine theta equals 1/3, and now figure out how we can solve for theta in this. Now notice that 1/3 is not one of our nice unit circle values for sine. If you review the unit circle, all the y coordinates on the terminal points, those are the sine values. None of them should be 1/3. So that simply means we're going to have to use the calculator. To do that, we'll go ahead and just say that theta equals sine inverse of 1/3. So let's bring out our graphing calculator to accomplish this. We'll say second and then sine for sine inverse. And then we want 1/3, 1 divided by 3, close parentheses for the input. So we have sine inverse of 1/3. If I hit enter on this, it'll give us the value of 0.3398369095. Okay, so we'll probably just round this, but that's the value provided in the calculator. We'll just call that maybe 0.34 if we round it to 100th. Or you actually might see a lot of trig books using more decimal places to be more accurate. So you might see them using like 4 or 5 decimal places. If we used 5, this would of course be 0.33984. So we'll just go with that to give a little more accuracy. Some books will do that just as well. Now, you may recall from some of the other problems we've been doing that you have to account for more than what you might see in the most simplistic form. So here's what I mean. I'm going to go ahead and just sketch a little diagram in our corner here, a little unit circle, and we'll put it on the coordinate plane so we can just kind of mark what we're dealing with here. As we know from the unit circle, the top of it would be pi over 2. Now, pi over 2 is approximately 1.57. If you had to just estimate, right, 3.14 divided by 2 is approximately 1.57. That would be at the top of the unit circle. So we're at 0.33, which is certainly less than that. You might also kind of estimate some just reference places here, like in the middle of quadrant 1, at the middle marking on our unit circle, you'd have pi over 4. Pi over 4 is approximately 0.785, which is clearly still bigger than theta. We're just trying to estimate where theta is. So let's get down even a little bit further. Again, just using the values we know of on the unit circle. I'm going to try pi over 6, just because that's a familiar place to us as well. If I hit enter there, that's 0.52. Okay, so the value we have for theta is even less than that. It's pretty tiny, which means it's pretty low in quadrant 1. I'm going to estimate it just with a point, and it's pretty low. We're going to call that little value, that arc value there. This is our 0.3398. Why are we doing this? Well, because notice the symmetry of the circle. Our arc, or you could say our angle, from the center of our unit circle to this place we just marked is pretty small and thin. It's not a very large angle, but it would be symmetrically the same sine value on the other side of the unit circle in quadrant 2. So what I'm going to do is go mark a place over on the other side in quadrant 2, which would be symmetrically the same distance. Now, if you think of it this way, 0.33984, that's how far we extended beyond the x-axis from our normal beginning place on the right side of the unit circle. We extended 0.33984 just a very little bit to get to the theta value we just used as the sine inverse of 1/3, right? Well, that same distance, symmetrically speaking, we will want to rise on the other side of the unit circle, the left side, rising from the x-axis over there, so we get the symmetrically same y value, which is what we're looking for the sine function. So how do I know how far that is? Well, all the way across would be pi, that is on the left side of our unit circle, but then I would be subtracting, since we would be going kind of backwards, upward, clockwise, I would be subtracting the same thing. So so let's mark this as pi minus 0.33984. That's how far the angle is on the opposite side, rotating upward to the symmetrical place. All right, so there's a lot of detail there. It might help to kind of draw it out on your paper clearly and largely so you can see it and believe it and use it. Use a calculator to kind of make sure you're getting the same values that I am as well. So here's the point. That other value for theta is a valid solution, right? We're looking for a sine value, the sine inverse of 1/3, and we know that sine is symmetrical, so that values in quadrant 1 are the same as values in quadrant 2. They're both positive values for sine. So we can say that theta is also then pi minus 0.33984. We have two values for theta here. But then furthermore, we know that we could add any period of sine to these, or any multiple of the period of sine, to get other values, as we've been saying. So if we add 2k pi to each of these, since the period of sine is 2 pi, 2k pi, where k is an integer, represents then adding or subtracting any multiple of 2 pi. Any multiple of the period will take you back to a solution of the same sort as we've been seeing. So we have here one side that gave us nothing, the sine theta equals 2. We know that couldn't happen, so we just ignore that. But then we also have these now sets of infinitely many solutions, 0.33984 plus 2k pi, and then pi minus 0.33984 plus 2k pi, which we could use to represent all the solutions. All right, let's go on to a third example. This one begins as follows. Sine squared theta on the left side all by itself equals 2 sine theta plus 3, and that's on the right side. We want to solve this for theta, kind of like we've been doing. Now, you'll notice that it's not quite in a convenient form yet. So what we're going to do is start by moving everything on the same side, and I want to move everything over to where the squared term is already positive. So on the left side, I want to leave that there, but I want to subtract 2 sine theta from both sides, and I want to subtract 3 from both sides, which will move everything over to the left side. So on the left, we'll now have sine squared theta minus 2 sine theta minus 3, and that's all equal to 0. So we're subtracting 2 sine theta, and we're subtracting 3 really from both sides of the equation. There's the result. Sine squared theta minus 2 sine theta minus 3 equals 0. Well, hopefully this is looking a little bit familiar enough to the previous problem that you might follow our next gesture here, which is to estimate, or not estimate, recall with algebra. If I just simply let the sine theta be the letter a, then this is really like a squared minus 2a minus 3 equals 0. And actually, let's move this over to the side so we don't get too confused. This is what we're recalling just from algebra that we're going to utilize for our current problem. If I had a squared minus 2a minus 3 equals 0, this is just some simple trinomial factoring. It's even simpler than the previous one we did. This would be an a times an a in front, and then you need two values that add to negative 2 and multiply to negative 3 for this case. To do the guess and check, you could say a minus 3 and then an a plus 1. Again, guess and check would mean you could FOIL those or multiply those together to make sure you're getting the actual expression previously from it, now in factored form of a minus 3 times a plus 1. That's all equal to 0. Okay, so if we go back then to our trigonometry to the left, where we had, and substitute now what we know the factoring will work as for these. So instead of our equation sine squared theta minus 2 sine theta minus 3 equals 0, we're going to use like the a minus 3 will be sine theta minus 3, or the a plus 1 will be sine theta plus 1. It's just doing the factoring off to the side. You don't even really have to do the letter A simplification of this. It just kind of helps people sometimes to feel less cluttered, but if you get comfortable with it, you can just kind of jump right to the trigonometry to get these factored. Now, if we use the zero product property for these two factors, which are now multiplied to get 0, so it does apply, we'll get two possibilities. We'll have the first one, which would say sine theta equals 3. If we set that equal to 0 and then add 3 to both sides. But as you already recalled above, you cannot have a sine value beyond 1. That's the range of sines, so there's no way we're going to get a solution from that branch. We'll move on to the other one where we had sine theta plus 1. Of course, if that equals 0, let's write this out. Sine theta plus 1 equals 0 for the zero product property here. This would mean sine theta equals negative 1 if I subtract 1 from both sides. The question is, where does sine theta equal negative 1? Well, this is actually a nice simple unit circle recollection. Sine theta is only negative 1 in one place. That's the bottom of the unit circle. And so where is that place? Well, again, if you're kind of just counting it with radians, you're starting on the right side at 1, 0, going all the way around till you get to the bottom at the point 0, negative 1. That would be 3 pi over 2. So we could say theta equals 3 pi over 2, also known as 270 degrees. You can review the unit circle to catch where that comes from. Now, that's the case for this one circle, within one wrap of the circle. That would be a solution, but we're trying to account for all of them. So, of course, we're going to add the multiples of the period either way to get other solutions. Since the period of sine is 2 pi, we'll just say then plus 2k pi, again, where k is an integer. Also represented by the script z. So we'll say k is an element of the integers, and that's our solution. All right, let's do one more example. This one's number 4, and it begins as follows. On the left side of our equation, we have 3 tan theta sine theta minus 2 tan theta, and then that's equal to 0 on the right side. Now, if you take a look at this, you'll notice that there is a common factor going on. There's a tan theta in both of the terms on our left side. So that might be motivation, as you may recall from algebra, to factor out that common factor. So what if we did this? We take a greatest common factor out. Let's see, I'm just going to write this as tan theta, that is that common factor. But then if I factor that out of the terms that are there, we're left with 3 sine theta for the first term minus 2 for the second term, right? What we're saying is if you distribute this tan theta into those in parentheses, tan theta times 3 sine theta, tan theta times -2, you're going to get that original left side, which means you can simply factor out the tangent theta, which is convenient because now we have a product equal to 0. That's a place we want to be because now we can use the zero product property. So this tells us we have tangent theta equal to 0. That's one of its factors. The second factor was the 3 sine theta minus 2 equal to 0. Let's solve each of these and see what happens. So in the first case where you have tangent theta equal to 0, remember tangent, we did I think redraw these tangent values on the unit circle in the previous topic. You can review that or redraw them yourself or look at your unit circle. Tangent is equal to sine over cosine. The question is, where is that equal to 0? And actually it's in two places. It would be on the right side of the unit circle or the left side of the unit circle. In those places, the coordinates are 1, 0 on the right side or -1, 0 on the left side. And if tangent is sine over cosine, also known as y over x, you're getting 0 over 1 or 0 over -1. So in those cases, tangent theta is equal to 0, which means within one wrap of the circle, we're looking at theta being 0 or theta being pi. That is the right side or the left side, right? Okay, we'll hold on and actually let me just list those separately so we can have a little more space to write, but we'll hold on to that for a second. Let's go to the other branch for now and get some further distance on that one. If I take the 3 sine theta minus 2 equals 0 that we had, and we solve for sine theta like we've been doing by adding 2 to both sides first, this will give us 3 sine theta on the left side equals 2. To get sine theta by itself, of course, we'll just divide by 3 on both sides. This gives us then sine theta equals 2/3. Now, 2/3 is not a recognizable, nice unit circle value for sine. We'd be looking at the y coordinates of all our terminal points. You'll find none of them to be 2/3. Well, that's okay. By now we know we can just use the calculator to get a value for theta. We'll have to just estimate it with a sine inverse there. So let's do that. Let's take out our calculator. And this time we want second sine for sine inverse. And I want that of 2/3. So 2 divided by 3, close parentheses, hit enter, and it's going to give us 0.72973 if you wanted to round it to 5 decimal places there. All right, so let's write this down here and then also think, as we had to do in a recent example, about how the symmetry of the unit circle applies here. So if I just break out another unit circle, let's figure out where this value is, 0.73 roughly, right? Now, we kind of recalled some of this stuff earlier in number 2 above, right? We kind of recalled that at the top of the unit circle, pi over 2 is really about 1.57. Pi over 4 is about 0.5. No, I'm sorry, it was like 0.8. 0.8-ish. Pi over 4 right there in the middle of quadrant 1. We were just getting some decimal approximations there just to have a sense of where our angle is, or our arc. So in this case, we're looking at 0.72. And just think of it. At the top, if it's 1.57, halfway up quadrant 1 is 0.8, roughly. So 0.72 is just a little bit less than that. So we'll just kind of estimate somewhere in quadrant 1. That would be where the angle, or the arc, for our case here, 0.72973 is approximately a little bit less than halfway up that first quadrant. Why does it matter? Well, because we care about the symmetrical values. For sine, remember, you might get you would get a symmetrically equivalent value in quadrant 2. If we start on the left side, which of course is pi, according to our unit circle, then we rotate clockwise up to the symmetrical place for this angle, which is a distance of what we already got, the 0.72973. That means this other place would be pi minus 0.72973. Or I suppose you could estimate that as just 0.73 to be a little bit easier. But the point is that symmetrical place is another place where you're going to get the exact same value for sine. Why? Because those two have the same y value symmetrically on the unit circle, which means you're going to get another solution. So we'll say theta here is approximately pi minus 0.72973. Both of those are valid solutions within one wrap of the circle. Now, as we've been saying or doing, you want to account for all the solutions, so we have to now get into the periodic nature to describe the rest. We go back to the first set of solutions we got from our first branch. We got theta equals 0 or theta equals pi. Well, let's recall here that the period of tangent is pi. So since that is the case, let's just kind of recall the period of tangent is pi. The reason that matters is because I would normally say, okay, 0 is my first solution, therefore 0 plus k times pi to represent all the rest. Well, guess what? That's going to catch or pick up the other solution of pi, right? Because when k is 1, then 0 plus 1 pi is pi. So if I write it as 0 plus k pi, that represents the next solution. But if I write the next one as pi plus k pi, then that's going to represent the same batch because I'm just adding multiples of pi to 0 or pi or 2 pi or so on. So actually, the overall result, the summary of all of that would just be k times pi, because that will represent both original solutions and all those thereafter, with k being an integer. Since these overlap, one of them will pick up the other one and everything else. But in the other set that we just got, we're going to have to do these separately because these don't overlap. You can verify this on a calculator. Even though we're using nasty approximated decimals, you can still see it there, which is that when you take the first solution of 0.72973 and you add the period of sine with a multiple of k, so it would be 2k pi or 2 pi k or k2 pi, anything like that, where k again is an integer. K is an integer denoted with the script z. Then if you take 0.72973 and start adding multiples of 2 pi to it, you're not going to hit the second. So these don't overlap, which means we're going to have to do the same thing for the second one to represent it, going on forever. So plus 2k pi. And so then all of this would be our solution. The k pi from the first portion, and then these two other expressions where you have 0.72973 plus 2k pi and pi minus 0.72973 plus 2k pi.